Assalamu alaikum everyone. Today we are going to conduct lecture number 17 of our online course about microprocessors and assembly language. And today's topic is machine code conversion. So let's proceed to the topic. Okay, what is machine code conversion? It is simply translation of assembly language into machine codes or binary data which can be understood by microprocessor. So machine code is simply translation of assembly language into machine code. Each instruction is translated at once. Machine code will specify following things: what operation is supposed to perform in the instruction which is given in assembly code, what opcode is to be used, what is the key mnemonic that should be used in assembly instruction, and whether the operation is 16-bit or 8-bit. We have already seen addressing mode lectures, and in that we learned that in each instruction it is given that operation is going to be either 16-bit or 8-bit, so that must be also specified in machine code. So microprocessor must understand that he's performing 16-bit operation or 8-bit operation. Okay, the next thing which is going to be specified in machine code is about the operands, where these operands are stored. Either they are stored in register or they are stored in the memory location. So this is again a very important specification which is provided by machine code. All these informations are in forms of ones and zeros. We understand because we are talking about binary language which is understood by microprocessors. So all this information, whether we are talking about operation or the opcode or the operation size or the location of operands, these all information must be in ones and zeros. Machine code of each instruction vary in terms of number of bytes. This thing we have also experienced while we were doing some examples of addressing modes. We understand that there were some instructions which were just combination of 2 bytes, or there were some instructions which were made up of more than 2 bytes. Some instructions were involving more than 3 bytes, even 4 bytes were involved. So these machine codes of each instruction vary in terms of bytes. Some of the machine codes will be combination of 2 bytes, 3 bytes, and so on. Okay, the maximum size which can be experienced in machine code is 6 byte in 8086, and this thing we have already explained in earlier lectures. Okay, in this slide we are going to discuss the format of machine code. An instruction can be coded up to 1 to 6 bytes. That means maximum size of machine code can go up to 6 bytes. So byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, these are basically format of machine code. So we are going to discuss byte 1 here. Byte 1 contains 3 kinds of information. We can further see here, look, 6 bits combination, and that is called opcode. We already know opcode field is of 6 bits, and it specifies the operation code, whether instruction is demanding addition operation, subtraction operation, or data movement, or any other operation. That operation is coded in these 6 bits of opcode field. The next bit is direction bit, and it is just 1 bit. One can see here. So these direction bit, it tells about the register operand which is in the second byte. So this is quite interesting. This register operand, and it is 3 bits operation, and it is related with D. So D bit tells us about register operand and specified by reg field, which is present in the second byte. Remember, this is our first byte, this is our second byte. So reg field, which is present in the second byte, it is a 3 bits field and it is related with d bit. So d bit tells about the register operand, and that d bit would be simply 0 if we are encoding a register as a source, and that d can be 1 if we are coding a register uh, as destination. We're gonna see these things in detail. In summary, we can just simply say d can be 1 or 0, and it depends upon register of reg field. Reg field encodes a register. If that register which is encoded in reg field is going to be source operand, then d will be simply 0, and if reg field encode a register which is a destination register, so d will be equals to 1. The next thing is data size bit, that is w bit. It specifies about the size of operation, whether the operation will be 8 bit or 16 bit. When we were learning about addressing modes, we come to know that it's quite possible that microprocessors assembly code or assembly instruction is performing only 8 bit of information or 16 bit of operation. So that 16 bit or 8 bit operation is specified under this bit. So whenever w bit is equals to 1, it means it is a 16 bit operation, and if w bit is equals to 0, then it is 8 bit operation. In this slide we are going to discuss byte number 2 of journal instruction format. So this is our byte 2, and it has again 3 fields. First field that we discussed in the last slide as well, that is register field, and it is of 3 bits field, is used to identify the register for the first operand. So it can actually encode any register operand, and it is connected with d bit in the byte 1. We have discussed this point as well. If remember, d will be 0 if this register is going to be source register, and that d will be equals to 1 if that register is a destination bit. So the second field in this byte 2 is basically register slash memory field, and that is also of 3 bits, and that is this one, register slash memory field, and it is again 3 bit field. It specifies the second operand. So basically these two things, register and r/m's, these are specifying two different operands. First we discussed about reg field, it specifies only register operand, and this field now r/m or register slash memory field, it specifies second operand. It can be a register or it can be a memory as well. That is why r/m is being used here for its name. So it is connected with the mode field, and it is connected to mode field like this. So how it is connected, we are going to discuss it in coming slides, but we must know that reg field is connected to d field and r/m field is connected to mode field, and mode field is combination of 2 bits, and we are going to see what are possible options available for mode field. Okay, in this slide we are going to discuss about possible options or possible combinations which are present for reg field. As we remember, reg field is 3 bit field, and it can actually create 2 power 3 equals to 8 different combination. I hope you remember the combinations thing. So 2 power 3 will be equals to 8 different options, like we can see here 0 0 0 1 0 1 0, and it goes up to 111, and we are just naming them by associating these numbers with certain registers. For example, 00 can be AL, 001 can be CL, 010 can be DL, 011 can be BL, 100 can be AH. So these are encoded combinations for these registers. And if you closely look at this column indicates only those registers which are just of 8-bit. So that is why W equal to 0, the size operation or size bit is equals to 0. That means these are just 8-bit. But in case if we are dealing with size equals to 1 or W is equal to 1, that means we are dealing with 16 bits. So these 8-bit register can be converted into 16 bits. So this 00 in 8-bit it was equal to AL, but this 00 becomes AX whenever we are considering W equal to 1. Similarly, 101 was associated to CH in W equal to 0, but if we are considering W equal to 1, so this 101 is associated with base pointer. So these are different codes, and we are going to use these codes while we are going to convert our assembly language code into machine code. Okay, this slide we are trying to deal with the possible options of mode field, and mode field was combination of 2 bits, so we have only 4 options: 0 0 0 1 1 0 1 1. 0 0, it tells us about the mode operation, that it is basically memory mode, simple memory mode without any displacement, and we're gonna see what is it without displacement. Then 0 1, it indicates memory mode but with 8-bit displacement. 1 0, it is again memory mode but with 16-bit displacement. So one can see that no displacement, 8-bit displacement, and 16-bit displacement. And 1 1, it is again totally different. These were 3 different memory modes, but now we are talking about register mode. And of course we know that in register mode there is no need of displacement, as displacement is concerned only with memory mode. So 1 1 is totally on register mode. So these are different encodes we are going to use in assembly code conversion into the machine code. Let's see how we will use them. Okay, before we proceed further, we need to deal with the last table as well, and this is the table that you will be using whenever one is going to ask you that you need to convert any assembly language into machine code. And we have seen different parts of this table separately, but we are going to collect all those information in one table. So this is the one table. If you know it, these tables, so you can easily convert any assembly language into machine code. So remember, first of all we should start with the mode. Remember, we have mode 0 0 with no displacement, mode 0 1 with 8-bit displacement, mode 1 0 with 16-bit displacements, and then this table mode 1 1 is register mode, so no memory mode. And before we proceed further, we can simply say that mode 0 0, when there is no displacement, we may point our memory with base plus index, as that index can be SI. So remember, base plus SI, base plus DI, simple base pointer plus SI, base plus destination index. So these are memory mode without any displacement. Again, it can be simply index mode as well, so SI, DI. And if we are using direct address, so again there is no displacement, again direct address is given, and base register is given. So these are options available, and these are how many options? These are 8 operations or 8 options. So we encode them in 3 bits, 0 0 0 0 1 0 1 0, and it goes up to 111, and it is encoded in r/m field, and we gonna use it so you will understand it more. But we know that this r/m indicates these things. If mode 01, then 001 will correspond to this thing, base plus destination index plus D8, since it is an 8-bit displacement. Similarly, 001 r/m, and if we are considering mode 10, so this will refer to base pointer plus destination index plus D16, which is displacement of 16-bit. And if we are not using any memory mode, we are using simply mode is equal to 1 1, then we can actually use only register So one register can be AL if W is equal to 0, and then this will be coded as 000, and if W is equal to 1 and our register is stack pointer, so the value of operand will be 100. So we are going to use this table, and using this table we are going to convert it. Let's proceed to the exact conversion that we can see. Okay, this is our very first example that we are going to translate into machine code. Move BL comma AL. I hope everybody understand this instruction now, since AL is a source register and BL is going to be destination register. So whatever the content of AL, it is going to transfer inside the BL. So let's proceed to its machine code conversion. First of all, we need to think about byte 1, and byte 1, the very first field that we need to discuss is opcode, and opcode will always be given to you. So we don't need to remember them. If you want to know where it is given in your book, it is in 3.6 figure in instruction set. You can actually look for different opcodes, but whenever you are going to ask, you are asked to calculate any machine code conversion, so this opcode will be given to you, so we don't need to worry. So opcode for move is 1000010. One can see that this is basically just 6-bit 6-bit information. So this is opcode, it is given. Next thing, we know that AL is a register, so we are going to encode this AL as a register field. We remember for register, and if we are going to encode AL, so register will be equal to 00 according to that table. I will recommend you, while you watching this video, you must note down that specific table, or I have already uploaded on your portal, so you can use that table so that you understand it clearly. So register is equals to 00 if we are encoding AL in that register, and since AL is a source register, that is why D will be equals to 0. Remember that thing we discussed, whenever register field or reg field is encoding a source register, so since AL is a source operand, so D will become equals to 0. One thing more, W bit will be equals to 0 because it is AL, and AL is just 8-bit register, so W will be equals to 1. If it was AX, so it will become 1, but this time it is just 8 bits, so W bit will be equal to 0. So I think first byte is complete. First byte, we can see that first we write opcode, then we write D bit, then we write W bit. So first opcode, then this D bit, and then this W bit. I have just gathered them, so I just converted them into hex. It becomes 1000 equals to 8 and 1000 equals to 8. So that is why byte 1 is equals to 88 hex. I hope this point is clear. Now we're gonna discuss about mode. Mode is equals to 11, or it is register mode. We don't see any memory operand here. These both are what? Registers. So second operand will also be a register. That means mode will be equals to 11. So r/m would be equals to 011. Why? Because second operand is BL, and when we are going to encode that BL in r/m, you see BL will be equals to simply 011. So byte 2 is complete now. Byte 2 is combination of mode, register, and r/m. Mode value is 11, register is a 00. Remember that thing we have already mentioned while we were deciding byte 1. Then 0111, it is the value of r/m. We just decided it. So if we just put them in order and we code them, it is 1100, that means it is simply C, and 0011, that means 3. So our machine code is basically 88C3. These are 2-byte instruction. One can see first byte is 88 hex and next byte is C3 hex. So the complete information will be 88C3 hex. Okay, in this slide we are going to take again same example, move BL comma AL, but this time we do the second method, or another approach we could use for conversion of this assembly instruction into machine code conversion. First step is similar. Opcode for move is 10010 and it will be given, so we do not need to worry. So there comes to different approach. Last time we encoded AL in REG field, but this time we are going to use PL in REG field. Since both of these are registers, so any one of them can be used for to be encoded in REG field. So last time we used AL for REG field, and this time we are going to use BL in the REG field. So this time BL is encoded in REG, and according to table, I hope you have seen that table, and still you are able to see the table in the book, so or in the uploaded table. So BL is equal to 011 whenever we are considering REG operation options. And this time BL is a destination operand, we can see that, so D will be equals to 1. Remember in last slide when we were considering AL in REG, AL was source operand, so we make D equals to 0, but now BL is destination operand and it is being encoded in REG field, so D will become equals to 1. Now size of operation, it is simply 8 bits, so there will be no change in size bits or W bit will be equal to simply 0. So byte 1 is combination of opcode, D and size bit, so we are going to just put the values, that is our opcode, that is D bit, that is size bit, and now we are just going to arrange them in hexadecimal. So 1000, that means 8, and 1010, that means A. So the first byte is 8A hex. Now let's come to the mode field. It is going to be again register mode because both of these operands are registers, so mode field is simply 11. So r/m would be for the next operand which is not encoded in the REG. BL is encoded in REG, so remaining operand is AL, so AL will be encoded in RM or r/m field, and the code for AL is 000. You can further confirm these values in the table. So byte 2 will become mode REG r/m, mode is 11, we see this value here. REG is equal to 011, so it's 011, and then it comes to r/m, so r/m is 000. So now we just arrange them in 4 bits order, so 1010 and 1000. So 1101, that means D, and 1000 means 8. So that was our first byte and that is our second byte. So our complete byte or machine code will be 8A D8 hex. So again it is a 2-byte instruction. I hope this is clear. Okay, in this slide we are going to take one extra example, that is move CX comma DX. So let's proceed to the machine code conversion. Again the opcode for the move is same, which is 100010, and it will be given, so we do not need to worry about it. Second thing, we need to decide a register field. So let's say we are encoding CX in register, so CX code is 001 in that table. I hope you can see it. And since CX is our destination operand, so D will be equal to 1. Remember, if register field is encoding source operand, then D will be equal to 0. If register field is encoding destination operand, which is the case in this example, so D will become equals to 1. The next bit is size bit or W bit, and that is equal to 1 because it is a 16-bit operation. In earlier two example we discussed was 8-bit operation, so W bit was simply 0, but right now in this example it is a 16-bit operation, so W bit will become equals to 1. So byte 1 will be opcode, D and W. So we just put the values. This is our opcode 100010, and D bit is 1 and W bit is 1. So we are just arranging them in hexadecimal form. So 1000 means 8 and 1011, that means B. So the first byte is 8B. let's go to the mode. It's again register mode because both of these operands are CX DX are register, so no memory mode, so mode will be equals to 1 1. So since CX is already encoded in REG field, now remaining operand is DX, and DX is going to encode in r/m field, so that opcode is basically, or the code for DX is 010, and you can see in the table as well. So the byte 2 will become mode register r/m, so these are their values. Mode is 1 1, register is 010. Remember, register is okay, there is a mistake. Register is 001. Okay, let me correct it. Register is mode is 1 1, register is 001, and destination and r/m is basically 010. So we are going to just order them, so 1100 and 1010. So I hope you understand it. It is equal to C and it is equal to A. So there was a mistake, I just corrected it. So byte 2 will be CA, not T1, it will be CA. So complete information will be 8B, which is the first byte, and the next byte will be CA. So that is our 2-byte instruction. There was a mistake. I hope confusion is clear because I have solved it manually in this slide. Still, if you have any confusion, we can solve this example again in the online session. Okay, in this slide we are going to take one more example, and here it is move AL comma DI. So what is so unique about this example? We see here AL is a register, DI. Is it a register? No, it is not a register. It is a memory operand. So now we have only one register, so only one option for what? REG field. So there will be no choice. We have only one option, so AL will be encoded in register field. So first of all, first tab is move code, opcode, which is move for 10010. That is simple. The next thing is AL is going to be encoded in register, so value for AL is 00. It is given in your table. I hope you can see it. Since D will be equal to 1, since AL is destination operand which is encoded in register, since both of these are related, so D will be equal to 1. W bit, which is a size bit, it is going to be 0 because we are dealing here with 8-bit register, so 8-bit operation. So first byte will become opcode DW. The first byte is opcode is 10010. D is 1, W is 0, so it's gonna be 10000 and 1010. That means 8A is going to be our first byte. Okay, mode, it is going to be 00. This time it is not register mode, it is a memory mode, but no displacement. We don't see any displacement here, so it's a memory mode with no displacement, so mode will become equals to 00. The next thing is r/m. Since we have already encoded AL, so DI will be encoded. I hope you can see in the table DI is encoded as 1010, so r/m is equal to 1010. So byte 2 will be mode, mode is 00, register, register is 000. Look, we have encoded it. R/m, which is DI, it is R101. So once we arrange them 4 times 0, 010, so it becomes 05 in hex. So the total machine code for this assembly instruction will be what? 8A, which is this first byte, and 05, which is the second byte. So it's again 2-byte instruction. I hope you have understood this machine code conversion. Okay, in this slide we are going to deal with another example, and this time we are using some different command instead of move command. So command is add, which is our mnemonic. So it will be given, opcode will be given for it. So opcode for add is 6 times 0. It will be given in the table, so we do not need to worry about it. We have to worry about these operands. So this is our first operand, which is bx di plus 1 2 3 4. I think you understand it. It is a memory, which because we see brackets here, square brackets, and it is base indexed mode because we see base, index, and displacement part. And the second option, the second operand is AX, which is simply a register. So AX is going to be encoded in REG field. So AX is encoded in REG field, and the code for AX is 00. Since D is bit is related with REG and AX is a source operand, so D will become equals to 0. W bit, it will be equals to 1 because AX is a 16-bit register, so this will be a 16-bit operation, so W bit is equal to 1. So opcode is the byte 1 will be opcode D comma W, so opcode, then a D bit, and then a size bit. So if you arrange them in hexadecimal form, it becomes 01 hex. I hope this is clear. Let's proceed to the next thing, and this is going to be memory mode because we know it is a memory operand which is involved here, and this is memory mode with 16-bit displacement. So a mode option will be chosen 10. You can see in that table mode will be 10 because it's a memory mode with displacement r/m. We have already encoded AX. We need to encode this BX DI plus 1 2 3 4, and if you see in that table for BX DI and 16-bit, that is supposed to encode in r/m. So r/m combination for this particular option is 001. So our byte 2 will be mode reg r/m. Mode is 10. Reg is 000 from this thing, and r/m is 001 from this thing. And so if we arrange them in order of hexadecimal, so it becomes 81. I hope this point is clear. One thing more, we see here information is still not completely encoded in machine code because this displacement which is given in the instruction must be encoded. So we see 1 2 3 4 hex. So we are going to use that general instruction format. So this is going to be our lower displacement and this is going to be our higher displacement. So byte 3 will be our low displacement, which is 3 4, and byte 4 will be our higher displacement, which is 1 2. So complete instruction, complete machine code conversion will be composition of 4 bytes. Byte 1 that we encoded as 01 hex, and byte 2 that we encode as add 1 hex, and byte 3 is low displacement, which is 3 4. Byte 4 is high displacement, which is 1 2. So therefore the complete machine code conversion will be 01 81 3 4 1 2 hex. So this is a 4-byte instruction. I hope we have covered a very important example in this slide in which we learned about memory board with 16-bit displacement, how we are going to encode that specific instruction into machine code. Furthermore, how displacement thing can be arranged. So I hope if you practice it yourself, you will be master of it. Okay, when we talk about practice, so we must have some practice problems. That's why in this slide I have mentioned some of the practice problems. If you do practice of these things, hopefully you will be able to understand complete essence of this machine code conversion. So these are your 5 different examples. I hope you can solve them, and once you have any problem, you can note them down so that we can discuss in online session. One thing which can be noticed here, opcode for these instructions which will be given for given in figure 3.6, or furthermore some of the opcode I have already told you in the slide. So if you need opcode, go and look for in figure 3.6. You will find each and every opcode for instruction. Okay, that's it from this lecture. Today we covered a very important topic, which is machine code conversion, how one can translate assembly code into machine code or the binary code. I hope I have explained things in detail. If you have any query, please note them down. We are going to deal with them in a question answer session. Thank you so much.